Okay, so time to get started here. Good morning, everyone. I'm going to be starting out somewhere near the end of the slide deck, or actually quite a ways into it. I think hopefully these slide numbers should match the ones that you have. If there's any discrepancies, let me know. I added some additional slides, but I kind of fudged things in the LaTeX, so hopefully the slide numbers should match up. That should make things easier for you to find them if you're trying to find them. Anyway, so I'm going to start out the course by talking a little bit about algorithms and data structures. The algorithm stuff we'll get through today, and maybe data structures part of the next lecture, maybe part of the subsequent lecture, just to try to bring everyone sort of up to the same basic level. For those of you with a computer science or a software engineering background, probably a lot of this stuff is review, or I'd imagine a lot of this stuff would be review. But likely there's some things that maybe you haven't really stopped to think about, like some new spins on things. And for some other people from different backgrounds, this might be entirely new to you. So I want to try to make sure everyone sort of has a reasonable background in this area. So with that said, I'm going to talk about algorithms first. So in terms of software performance, there's two kind of performance measures that we're maybe most commonly interested in, which is basically time complexity and space complexity. So time complexity is just the amount of time it takes for the code to execute. Space complexity is the amount of memory that's required for the code to do its job. There's other criterions as well that we might be interested in software performance. I've listed some of them at the bottom of the slide. We might be interested in things like resource utilization, like how fast we can pump data across a network, if it's a network-based application, and so on. But predominantly, the most common things that we're interested in are sort of very pervasive are time and space complexity. What else do I want to say about this slide? When we're actually designing things, I mean, the reason for wanting to cover some of this material, make sure that everyone has this sort of background, it's quite fundamental. If we're worried about efficiency, we want to make sure that we have sort of a grounding about how we can quantify or try to get a sense of how much time, for example, an algorithm is going to take when it runs and so on. So these are some of the basic issues that I want to look at here. The first thing I want to talk very briefly about is what's called the random access machine model. RAM here, it doesn't have anything to do with random access memory. It's a bad acronym. It kind of overloads with other acronyms. But basically what it is, it's a very, very simplified machine-independent sort of model which we can use for the purposes of doing complexity analysis. So basically what it assumes in a nutshell is you assume a single processor. There's no multiple threads. Everything's run in a single thread of execution. There's no concurrent operations. You have two basic elementary types, an integer type and a floating point type. Each elementary operation, like each operation on these types, like for example, adding two floating point numbers, adding two integers, and so on, these all take one time unit. Elementary operations include things like arithmetic operations, like I just mentioned, like loads and stores, like reading and writing things, variables from memory. Branch operations, which are associated with control flow, like if statements, loops, and so on. Subroutine call, not the actual code in the subroutine, but the act of getting from the caller to the callee. That's basically like an operation like that. The actual subroutine call mechanism rather than the actual stuff that's in the subroutine. Loops and subroutines are not considered elementary operations. Like a loop is a whole bunch of elementary operations, so it's going to count as a whole bunch of operations. And subroutine, once you get into the subroutine and start executing the code there, the subroutine probably consists of a bunch of different operations. So the subroutine itself is not a single elementary operation. Hopefully that makes sense. And each memory access is assumed to take 1 unit of time. We assume unbounded memory. You can see this model is very, very unrealistic. We don't have infinite memory in practice, and access to memory can be very widely varying depending on whether we hit the cache or whether we have a page fault, etc. But it's a very simple model, and it serves the purpose of giving us a simple, tractable model that we can use for doing complexity analysis of algorithms and so on. So enough said about that. There's a number of different types of complexity measures we can use. Complexity is usually quantified or measured in terms of against the size of the problem. So for example, if we're sorting numbers, maybe we're sorting n numbers. So n is the size of the problem. It's the number of numbers that we want to sort. And then we're interested in how much does the time scale as we change n. As we increase the size of the problem, for example, how does the computation time go up, or how much does the memory that's consumed go up, and so on. And there's a number of different ways that we can quantify these things. The first is what's called the worst case complexity at the top of the slide here. This gives an upper bound on the complexity of the algorithm. So we might be interested in the worst case time complexity for an algorithm. Worst case is useful in situations like, for example, if you have a hard real-time application, you might be interested in the worst case behavior. If you're controlling a nuclear power plant, it's not good enough that you could respond to the potential meltdown. And if you need to do it within 50 milliseconds or everyone dies and there's a meltdown, it's not good enough. On average, you can respond in 50 milliseconds. You want to make sure in the worst case you respond in 50 milliseconds. So in some applications, you care about the worst case scenario. Also, there's average complexity. The basic idea is you take all the possible input problems that you can give, you assign probabilities to them, how likely they are to occur, and then you weight the complexity by these probabilities. Another type of complexity is what's called amortized complexity, which is involves a different type of averaging. Typically, this is used in situations where you have some operation that sometimes it may be very fast, maybe most of the time it's very fast, but every once in a while you take a massive hit and it's super slow. An example of this might be something like, for those of you who maybe know a little bit of C++, there's something called std vector. By the way, I just read this as std. It's a fairly common pronunciation of the std namespace, standard namespace in the standard library. Std vector is just a one-dimensional array, for those of you who are not familiar with it, but it's dynamic, like it can be resized. So if you try to put more stuff into it, there's not enough space, it will resize, it will allocate a bigger chunk of memory, and so on. And it will basically grow, it's growable. So there's a function called a member of this class called pushback, which can be used to add an element to the end of the container. And most of the time, this is very fast. It's a constant time operation because all that's happening is you have this big array, and it's just copying the element that you want to add to the end of the array. But every once in a while, what will happen is you run out of space. You try to add something to the array, but the array is already fully occupied. There's no more space. So what it has to do, the library has to do, is it has to allocate a new larger chunk of memory that's big enough to hold all the stuff that's already in the container, plus the new stuff you want to add to it. Then it copies all the elements over to this new chunk of memory, which could be a massive amount of work, because there could be millions or billions of elements already in the container. It's got to copy them all over. Then it adds the element that you want to the end, and then it has to get rid of all the stuff that's in the old container. So this is very, very expensive. But it only happens every once in a while, because typically the implementation is such that you're not going to be doing this every time you do a pushback operation. So in this sort of context, amortized complexity might be something of interest to you, where essentially what you're doing is you're averaging across many, many indications of the function. You're calling it maybe millions of times, and then saying across all those times, sort of on average, what's the behavior of the function. And for example, in the standard library, this pushback member function, it guarantees amortized constant time. So like across many, many calls, it behaves as if it's a constant time operation. But this is not the same as a constant time operation. Like in other words, the amortized is important. Sometimes it's really slow. Sometimes it's a linear time operation, because when it has to copy all the elements to a new bigger array, that's going to be proportional to the size of the elements in the container. So every once in a while, it takes linear time, but it doesn't happen often enough that the overall behavior amortized is linear. Instead, overall, it's amortized constant time. So that gives you some sort of feel about some of the different types of complexity measures that we might be interested in. And these things apply both to like memory and space and probably other things that we might want to measure as well. Asymptotic analysis of algorithms is what I want to talk about next. I mean, typically this is how a lot of analysis of algorithms is done, because in practice, there's so many things that could affect the actual wall clock time that an algorithm takes to run that it becomes very quickly unmanageable to try to analyze things in that way. Often when we're trying to design things, you want some sort of guidance in terms of how likely is it that this algorithm is going to be efficient enough for our purposes. And for this, we often use asymptotic complexity. So the basic idea with asymptotic complexity is we're interested in what happens when the problem that we're dealing with becomes arbitrarily large. So for the sorting example I was describing before, where the size of the problem n is the number of numbers that we're sorting, what happens when n becomes larger and larger, approaching infinity? It becomes arbitrarily large. Of course, in practice, things never are infinite. But what happens as things become larger and larger? And this is what asymptotic complexity analysis is interested in. And again, we're most interested in time and space complexity, but I suppose you could apply it to other things as well. The advantage of this sort of analysis is that, as we'll see later, it's kind of very manageable even for relatively complicated algorithms, whereas trying to say, like, what's the actual number of microseconds or milliseconds something going to take, it just becomes very quickly unmanageable to deal with, because there's so many things that could affect that. I guess the other thing I want to say about asymptotic analysis is that it does have some downsides to it. I mean, sometimes it can lead you astray, and I'll talk about some of the problems that you can encounter due to kind of some of the downsides of it a little bit later. A few things before we get into asymptotic, kind of the actual analysis of some algorithms as some examples. I need to introduce some notation. Again, for people, computer science background, I'm sure you've seen this before and had it beaten into you, and software engineers as well, but some other people might not. A lot of EC people, maybe you've seen it, you kind of know what it is, but not really. Anyway, so I just want to bring everyone up to speed. So there's basically kind of three notations. There's big theta, which is this guy here, big O, and big omega. And I just want to kind of introduce these different mathematical notations and give you a sense of what they mean. So these are used in asymptotic analysis. Basically what these things are, they're ways to quantify how fast a function grows as you go kind of asymptotically to the right on the graph, how like fast does the function grow. So we can talk about big theta of g, where g is some function. What this denotes is a set of functions that are basically these elements here are elements of theta g, and it's things that are upper bounded and lower bounded by an element, by the function g, up to some constant times g. So like all of the elements, again, f represents the elements in this function as a set of functions. It's all functions f that are bounded below by g times the constant and bounded above by g times the constant. So probably the better way to look at this is in terms of a picture on the next slide here. So essentially what we have is if this function f is big theta of g, it means that there's some constant times g that I can multiply by some constant c2 I can multiply g by, such that after we pass a certain point, which is n0 in this graph, everywhere to the right of this point, the function f is always below c2 times g. And similarly, it's also upper bounded by another different constant, c1 times g. So you can see that once we go past n0, in other words, for large values, again, it's asymptotic behavior for large values, in this case, values greater than n naught, this function f is always above this lower bound here. So it's sandwiching the kind of the complexity algorithm between two graphs. So this is very useful for establishing tight bounds on algorithms. It's tight in the sense it's lower bounding and upper bounding the behavior of the function. And then we have big O notation. Big O notation, it's a similar story, except the inequalities and stuff that we have are a little bit different. This is basically upper bounding a function. So if we have big O of some function g, this is the set of all functions, elements f, that are upper bounded. They're bounded above by a constant times g. So in terms of a picture, what we have here, so we have some function f, it's upper bounded by a constant times g. So once we go to the right of n naught, so once the asymptotic behavior kicks in, so we're sufficiently large in value, which in this graph is greater than n naught, you'll notice that f is always bounded from above by c times g. So this is the basic idea. With big O notation is you're actually putting a upper bound on things. So a big O notation is useful for upper bounds when we're analyzing algorithms. And then the last case was the big omega notation. This is useful for lower bounds. So when we have big omega of some function g, this is a set of all functions such that the elements in this set are always bounded from below by a constant times g. So in terms of a picture, which is probably the most helpful thing for understanding this, once we go to a sufficiently large value of n, something greater than n naught over here, we'll notice that the function f is always bounded from below by c times g. So this places a lower bound on f. So maybe I'll back up here. Just there's a few examples on these slides as well. Yeah, so we have, for example, for polynomials, which are very commonly occurring, often the expressions that we have when we're analyzing algorithms are polynomials. If you're interested in big theta of some polynomial function, so big theta of f is basically a function which belongs to big theta of n squared. This is an order n squared algorithm with respect to big theta. It's just given by the largest or highest order term in the polynomial. Because this term here is going to dominate all the others. When we let n go to infinity, the thing that's going to dominate is this. And you can show that basically it's bounded above and below by a quadratic n squared, just as an example. And then here, with big O notation, if we're dealing with polynomials, again, the thing that's going to be most of interest to us is the highest order power of n in the polynomial, because this is going to dominate when n becomes larger and larger. So this particular function here would be upper bounded by, or it would be an element of order n squared. It's basically going to grow quadratically as n becomes larger and larger. And then giving an example with big omega. Big omega is basically, well, if we have a function, for example, 5n cubed plus n, this is going to be an element of big omega of n cubed. It's also, it's upper or lower bounded by n cubed, but it's also lower bounded by n squared as well. But it wouldn't be upper bound or lower bounded by n to the fourth, because n to the fourth will grow more quickly than something that has n to the 3 as its highest power. And hopefully that makes some sense. I don't want to spend a lot of time on this. There's also some additional stuff that I'm going to skip over. There's small o notation and small omega. They tend not to be used so much in algorithm analysis. They're really used more for kind of mathematical derivations and stuff. So they're not really important from the point of view of this course, and you're not responsible for them. A little bit more about asymptotic notation. I mean, again, as I mentioned in the introduction of these different notations, like big theta of something is a set. It's a set of functions that satisfy some growth rate kind of relationship. So when we write, you often see people write things like f, some function f is equal to theta of something. I mean, strictly speaking, this doesn't make sense because f is a function. The thing on the left-hand side of the equal sign is a function. The thing on the right-hand side is a set. A set can't be equal to a function. They're not even the same type of thing. But often we write this just because it's, I don't know, it's just, well, it's the convention that people follow. I mean, strictly speaking, when we write this, what it really means is just f is an element of this set. So don't get confused by this. It's a common kind of abusive notation is to write equal sign. Actually, using this element of is probably more rare. Most people use the equal sign, but it means the same thing. The other thing is that sometimes you have like weird things like this where you'll just throw, you have like a formula and then you'll throw in a term like say big theta of n or big O of n or something like this. What this notationally means is it's as if well, really what you meant is something like this, where you have a function f, and this function has the property that it's an element of big theta of n. So what you do is you write this expression here, where essentially this is like an anonymous function. It's a placeholder for f, saying that the thing that's here, it grows with order like big theta of n. And this just helps reduce clutter in formulas, because this is kind of a bit overly verbose to write out, whereas this is much more compact. So this is a few notational things, just so that you're not confused by some of the stuff that shows up. Some properties of big theta, big O, and big omega. I won't go through maybe like the details of what the math is actually saying, but just summarize. I mean, basically these points here are just summarizing. The first three properties here are just saying that if you add functions with the same growth rate, in other words, they're either big theta or big O or big omega is the same, you end up with something with the same growth rate. It doesn't change when you add them together. You add two things that are, say, big O n, you get something else which is big O n. If you multiply by a constant, this doesn't change the growth rate. So for example, if we have something that, the function, if the function f, for example, the function f is like theta n, for example, then a times f would be theta n. Multiplying by constants doesn't affect the growth rate because of the way it's defined. And then if you multiply functions which have a particular growth rates, this just multiplies the growth rates. And I guess I have some examples at the bottom here. Like, actually, this I guess is what I was describing a moment ago. So like if f is a member of theta n, then also n times f of n would be order theta n squared. Because this thing here is order n, this thing here is order n. When you multiply order n times order n, you get order n squared. That's basically referring to sort of this property here. And I think that's really all I want to say about that. When we're dealing with logs, because of the properties of logarithm, we don't really care about the number base, because if you change the base in a logarithm, it's just the same as multiplying by a constant. And because asymptotic complexity analysis doesn't care about constants, it doesn't really matter. So the logarithm is, the base is typically omitted when we're talking about asymptotic complexity. With that sort of less interesting mathematical sort of stuff out of the way, just some practical comments about asymptotic complexity, just to kind of things to watch out for in terms of not using it in a way which is not really appropriate. The one thing that's important to always keep in mind is that asymptotic complexity deals with what happens when the problems become arbitrarily large. So you're basically saying the problem size is infinite. In practice, it's never infinite. But often it's still a useful thing to use this kind of analysis, because often, although the problem size is not infinite, it's large enough that the asymptotic complexity starts to kick in, and it sort of behaves, it's large enough that for all practical purposes, it's sort of as if it was infinite. However, that's not always the case. So sometimes you may not have that the problem size is big enough that the asymptotic complexity starts to kick in, and then all the analysis you're doing is going to lead you down the garden path, and you're going to make a lot of wrong conclusions about how things are going to behave. So just as an example here, so I have algorithm A, which takes a time, and someone's actually gone through the pain and figured out that it actually takes exactly these many seconds. If you run the algorithm, it takes 1 over 10 to the 10 times n squared seconds, where n is the size of the problem. Maybe you're sorting numbers with some fancy type of sorting algorithm. And then I have another algorithm B, which takes n seconds for a problem size the size n. According to asymptotic complexity, if we look at this, well, let's see, this is going to be like a taking quadratic time here. This would be like basically big O of n, or big theta of n, sorry, big theta of n squared, or big O of n squared. This one here is going to be linear, so like big O of n, big theta of n. So in terms of the asymptotic complexity analysis, it would lead us to conclude that this algorithm here is better. It's linear, this one's quadratic. However, as long as the problem size is less than 10 to the 10, which is a pretty large number, you can verify that this function here will give you a smaller number than this one here. In other words, in this particular case, if we knew that the problem size is always less than 10 to the 10, asymptotic complexity analysis will give us the wrong conclusion about what we should do, like what's going to be more effective. And basically the problem here is, again, asymptotic complexity analysis assumes the problem size is arbitrarily large. It never is in practice, but sometimes it's big enough that the asymptotic complexity kicks in. Here, it's not big enough to make it kick in. So that's one thing to watch out for. Always be kind of cognizant of the fact that, is the problem size really big enough that I can reasonably expect the behavior to be represented well by asymptotic analysis? Another sort of problem that you can run into is asymptotic complexity analysis hides constant factors. So for example, if I have an algorithm A that takes, for a problem size of size n, it takes n seconds, for example, and another algorithm B, which takes 1,000 times n seconds for problem size of size n, well, clearly, if you want the faster algorithm, you're going to pick the one that takes, n seconds rather than 1,000 n for a problem size of size n. But asymptotic complexity analysis will say both of them are equally good. They're both linear time algorithms, pick either one, flip a coin. But obviously, one of them is 1,000 times faster than the other, so you want to pick the faster one. So this is an illustration of the fact that constant factors are hidden by asymptotic analysis. So just kind of be cognizant of these things, because sometimes you can have algorithms where you have these, ridiculously large factors, like this is 1 versus 1,000, so they differ really, really greatly, and then this can really dominate the effect of how long things take. So asymptotic complexity basically gives us guidance, but we have to be kind of careful how we use that guidance and make sure that we're doing things reasonably. In terms of some common complexities that occur in algorithms, I've listed them here in this table in increasing order of badness. So the thing typically we like most is constant complexity. So in other words, the algorithm, regardless of how big the problem size is, it basically takes the same amount of time. It's independent of the problem size, which is kind of the best you can do. At the other end, we have like double exponential, which is like it grows really, really rapidly with respect to the problem size. And you can put these in order. These are ordered in the way that's shown at the bottom of the slide here. If you make n sufficiently large, these inequalities will hold down here. And God forbid you start to get into the territory down here. I mean, maybe you have in some of the courses you've taken, because there are some like graph algorithms and other things that maybe start to get into factorial. You've got combinatorial growth. These functions grow extremely fast, these ones down here. So you're into a lot of problems often when you're dealing with those sorts of algorithms, trying to make things take a reasonable amount of time, at least for any sufficiently large problem size. When we're dealing with algorithm analysis, often we encounter what are called recurrence relations. And basically what a recurrence relation is, it's just a definition of a sequence that's defined recursively. So we have like a sequence of numbers, which is denoted by f here, where n is the index number. And this is basically the Fibonacci sequence. That probably a lot of you are familiar with the Fibonacci sequence. It's basically the sum of the two preceding numbers in the sequence. So this is what we call a recurrence relation. And recurrence relations show up a lot of the time when we're analyzing the complexity of algorithms that involve recursion. So for example, if we were using a recursive formula to compute the Fibonacci function, which is a bad idea because it has very high complexity, but if you were to do it this way, if we try to analyze the complexity of the algorithm, we say, well, let n be the size of the problem be the number that we're trying to compute the Fibonacci value for. We're computing the nth element of the Fibonacci sequence. So n is going to be deemed to be our problem size here. How much time does the algorithm take? Well, if we look at the algorithm here, there's going to be some constant amount of time that's actually spent in this function itself, not counting the things that it calls. So we can denote that time by c. Then additionally, it's going to take the time required to solve a problem of size n-1 because it calls itself recursively. Plus, it also is going to take the time required to solve a problem size reduced by 2. So we have this Tn-1, Tn-2. So you see what we end up with here is a recurrence relation. So often when we're dealing with recursive algorithms, recurrence relations show up. And then the question becomes, well, how do you solve these relationships? If you're trying to figure out what is the asymptotic complexity of something that an algorithm is something like what's shown at the bottom of the slide, how do we do this? And there are lots of techniques for solving recurrence relations. Unfortunately, there's not any general approach that works for everything. Z transforms can sometimes be used for some things. Because essentially what we're doing is we're trying to find solutions to, sometimes solutions to like difference equations or things like this. There's also things called master theorem, Akbar-Bazzi theorem. And I'm not going to go into any of the details of any of these things. They're not really so important in terms of this course. Just the final results are the things that are useful. Maybe one thing to watch out for is sometimes you end up with expressions that look something like this in recurrence relations where n is the problem size, then you have like division by some constant, maybe like 2, like you have n over 2. You have to be kind of careful because if n is not even, then this formula doesn't even make sense because the indexes are indexes in a sequence, they have to be integers. So something that's sometimes overlooked when people are doing analysis is they just kind of ignore the fact that maybe there needs, like if bi is a 2 and n could be odd, then there needs to be like a floor or ceiling or something around this so it gets rounded to an integer. And then how does that affect the result, like the solution to the recurrence relation? A lot of the time it turns out if you just ignore this issue, you get the right answer, but it's not justified correctly, but you get the right answer sort of by dumb luck. Anyway, I've listed some solutions for some common recurrence relations here, and I've been kind of very careful to include floors and ceilings just to make sure things are kind of very strictly speaking correct. But if you ignore it, the good news is a lot of the time you kind of get away with it. You just stumble on the right answer. It's just that your justification is not valid. Anyway, the nice thing about this, notice that we're not actually solving for the sequence. Like I'm not actually trying to find out what the function, the sequence f is. All I'm interested in is what's its, well, actually, in some cases, I'm actually giving the function. But really what we're interested in is the last part. What's the complexity? And for some of these other ones here, like actually finding the sequence would be, I don't even know if you can really do it because some of them would be very complicated. But we're only interested in the complexity. Anyway, so that formula might be used, or that table might be useful for some complexity analysis, just so you can quickly look up in one place some of the common solutions to recurrence equations. There's a few slides I'm going to skip over here, just because there's a few more examples than really what I want to go through. But you can, from time to time, I will skip some of the examples and stuff in the slides, but you can always go back and look at them. It's not that they're useless, it's just that there's more examples than I really have time to cover. And some of them are maybe testing the same concept, so it's not kind of pointless to go through too many of them. So I have an example here where we want to compute the time complexity using like asymptotic complexity analysis of an iterative Fibonacci algorithm. So we're computing the Fibonacci number sequence. So the input to this function is just we want to compute the nth number in the Fibonacci number sequence. And we have some C or C++ looking code that computes this. And we want to do an analysis of the complexity. So basically the way this works is just for each line, we want to figure out like how much, assign some time to it. So for example, the first line here, line 2, there's going to be some copying of values into an array or something like this. So this is just a bunch of constant time operations added together, which gives us a constant, which I'll call C1. Then we have a loop on line 3. So this is line 3 here, we have a loop. Loops typically have two parts of them. There's like a fixed cost that you incur even if you don't loop. Like typically it's like initializing a looping variable or something. And then you have stuff that happens every time through the loop. So we have to be careful to account for this correctly. So the loop is actually going to be iterating n-2 times, assuming that n is greater or equal to 2. So we're going to loop n-2 times, and then the cost of doing things in the loop, if we look at what's happening inside the loop, what's happening on this line inside the loop, we have a fixed cost, which is I gets initialized to 3 once at the startup of the loop. So that would be like the fixed cost, which is associated with this C32. And then each time through the loop, we have to test the condition to make sure whether we actually keep iterating. But also, we have to increment this variable as well. So this would correspond to the C31. So we have like a fixed cost and then a cost that's incurred each time through the loop. And then each of the subsequent lines that are inside the loop, lines 4, 5, and 6, they're going to execute each time the loop is executing. So C4 is the cost of line 4, but it executes n-2 times because we're looping that many times, and so on. And we just continue the process for the remaining lines. And then C8 is just line 8 here, just happens once, we return at the end. So we have a cost associated with return, which is just some constant cost. Then we can sum all these things up in the table. If we sum all these things up, we end up with the mess at the bottom of the slide. And asymptotic complexity analysis is very nice because we don't really care about particular values for constant factors. So we add everything together, we get a constant times n plus some constant, and we don't really care what this constant is because whether this constant is 5 or 10, we still end up with big theta n at the end. Anyway, so this would be a linear time algorithm. In other words, big theta of n for computing Fibonacci numbers. Any questions? And then if we do space complexity analysis here, like how much memory is going to be used by the algorithm, it's a kind of similar sort of deal, but in this case, we're tracking variables, memory usage by variables. So in this particular case, we have like a local variable n, we have a local variable I, and we have a local variable a. So basically the storage cost is just the cost of n, a, and I. And none of them depend on the size of the problem, like none of them depend on n, so they're all just constants. There's no n factor involved. So we just have a constant plus a constant plus a constant, which is just another constant, which I'm calling a1, and therefore this is going to take big theta of 1. I mean, some people might write big O. A lot of people kind of interchange big O's and big thetas. Often they mean big theta. It's probably better to use big theta if you really mean big theta because it's more specific. It's a bound above and below, whereas big O is only telling one of them. Anyway. Then to kind of contrast this, if we do a recursive Fibonacci algorithm, as I kind of alluded to before, this is a really, really bad way to compute a Fibonacci sequence. If you try it, if you try to compute maybe maybe the 80th Fibonacci number, you're there for a bit of a wait. It's going to take quite a while because as it turns out, it has exponential growth in terms of the computation time. So if we kind of walk through this, I mean, for this particular algorithm, again, we're using n to denote the size of the problem so that the element in the Fibonacci sequence that we're computing, the nth element, is the size of the problem. And if we look at the amount of time that's going to be required here, we have some fixed cost that's associated with the stuff that's not calling the other functions, doing the recursion, calling Fibonacci n minus 1, n minus 2. So this is denoted by the C1 here. And then when we do the recursion, we have to basically solve the problem for one less problem size. So the problem size is one less, which is n minus 1. So this corresponds to this first term here. And then we have to also solve the problem for this problem size of n minus 2, which is this term here. And of course, we have the kind of less interesting case, what happens if n is equal to 1 or 2? In this case, then we're basically just hitting the return statement, which is a constant time when we return. But really the more interesting part is the kind of the top part of this, when n is greater or equal to 3. And if you go back and look at the earlier slide, which lists solutions to common recurrence equations, the solution to this is big theta of n to the n. So this is like a really, really rapidly growing function. As you increase the value of n, this function is going to get slow really, really, really fast. So this is a really bad way to compute Fibonacci numbers. The iterative algorithm we just looked at is much better. And then if we analyze the space complexity of this algorithm, actually it turns out this is much worse in terms of space complexity as well, compared to the iterative algorithm we just looked at. A common mistake I see with people who are kind of a little bit newer to complexity analysis and so on, you might overlook the fact that your first initial reaction when you look at this might be that it takes a constant amount of memory because you say, well, this function has a single local variable n, so it takes a variable n and you're done. But this is not the case because this function calls itself recursively. And so you have Fibonacci, the first Fibonacci invocation calls a second one, but when the second one's invoked, the first one still hasn't returned yet. So all of its local variables are still there, living probably on the stack. So as you recurse, if you have like n levels of recursion that are all in flight at the same time, you have n copies of all the local variables of that function. So like depending on the recursion depth, you're going to get that many copies of the local variables of the function. And it turns out for the particular code that we have here, the maximum recursion depth, like the number of function calls that are in flight at the same time due to recursion, I think is something like n minus 2. So that the important thing is it's order n. So the amount of memory that's going to be required is order n because each call of the function is going to require a constant amount of space to store n. But you have n calls in flight at the same time. So there's n copies of local variables. So although it might at first, if you don't think about it too much, it might at first look like this is only a constant time algorithm, or constant space algorithm, I should say. I hope I was saying space before, not time. Constant space algorithm, it's not. It's actually linear space because of the fact that each invocation of the function has its own local variables, and it's calling recursively. Any questions? Okay. And then the last part of this unit is just something that didn't really fit anywhere else, so I stuck it here. It's not really part of asymptotic complexity analysis, but it's something quite useful for trying to make judgments about whether to optimize things or not. It's referred to as Amdahl's law. So basically what this does is it says that if I have some kind of, maybe some piece of code that I'm trying to increase the speed of, I'm trying to speed up by a certain factor, it's trying to illustrate, well, there's a few things I'm trying to illustrate by this slide. They're depending on how much of the, suppose that you have some part of the code that you want to increase by a factor, you think you can increase it by a factor of 100. So you get really excited, like, wow, I'm going to really speed up the code. But if that part of the code only associated with maybe 0.1% of the execution time of the program, even if you completely eliminate that code, you're not going to change the speed of the program very much because you're optimizing a part which is responsible for such a small part of the execution time, it doesn't matter. And this is sort of what the bottom part of the slide here is saying. It's just trying to point out there's a upper bound. If you know that you can speed things up by, well, if you know something that the program is only spending a certain percentage of the time executing some code, there's a limit to how much you can speed it up. Even if you get rid of it completely, like you'll never be able to improve beyond that. If you're spending 50% of the time on a particular part of the code that you're trying to consider to optimize, and you completely eliminate it, which you'll never be able to do, like you get the execution time down to 0, you know that you can't speed the program up by more than a factor of 2, right? Because if it only spends half the time on this code, even if you delete that code, there's still the other 50% of the execution time that's not going to go away. So this is what the bottom part of the slide is pointing out, just that there's an upper bound. And this is a trap that sometimes people fall into when they get kind of over-eager to optimize. They start trying to optimize things, but they don't really, they do it maybe before doing any profiling the code to try to figure out where is the actual bottleneck. And then they spend lots of time trying to optimize some code. And in the end, it turns out that maybe only like 5% of the time was actually spent in that code or less. And then because of that, it doesn't really matter how much you sped it up. It won't really affect things too much. So this is useful for trying to figure this out. And maybe if I go up to the formula on the top of the slide, essentially what these different values are, FE represents the amount of time that's spent in the chunk of the code that you want to optimize. And then SE is the factor by which you think you can speed it up. And then SO gives you the overall speed up of the program. And the important thing to notice at the bottom here, there's this limit of how much you can speed things up, which is dictated by how much of the time is actually spent by the thing that you're trying to speed up. And this can also be applied to other things other than code, like hardware design and so on. But it's a very useful kind of thing. And there's an example here. So for example, at the very bottom of the slide, if it's 20, you have some chunk of the code you're trying to optimize and 25% of the time is spent in that code, and you speed it up by a factor of 2, the overall speed up of the program is only about 14%, like 1.14 factor. So it looks like great, like wow, I sped it up by a factor of 2, but the overall effect on the program, it might be important in your application, like 14% speed up, but it's not as much as it might look like at first. And if you had to do a lot of mangling of your code, because typically when you optimize things, you make the code a lot less readable, introduce much more possibility of bugs and so on, maybe the 14% speed up is not worth it, depending on what you're trying to do. Anyway, so that's all I have to say about algorithms. Any questions about any of that before we kind of change topics a little bit? Okay, so we're going to jump to another part of the lecture slides here, which is on data structures. I think this is just maybe like 5 or 6 slides later, so it's not too much further along. And what I want to talk about here are some, I'm not going to go through all of the section on data structures because it's quite extensive and a lot of it would be just review for a lot of people anyway. But I want to go through enough of it that I kind of cover the stuff that's more important and maybe make you think about some things that even if this is not completely new to you, maybe things that you hadn't quite thought about before, which are actually quite important. So first of all, just a bit of terminology. Again, for some of you, this will just be review, but we can talk about what's called an abstract data type. An abstract data type is just a specification essentially of the interface for some type. You maybe have some kind of container and you can add elements. There's an operation for adding elements, removing elements, maybe creating the container, destroying the container, stuff like that. The ADT typically specifies things like the general nature of what you're representing, like it's a container. And it stores maybe homogeneous, like elements of the same type. It's a homogeneous container. The set of allowable states it can have, I don't know, if it's a container, like it can be empty, it can be full, it can have some number of elements in it. The operations that can be performed on it, maybe you can add things, you can remove things, you can completely blow away the container, like destroy it, you can create a new one. And then maybe some specifications of preconditions and postconditions for operations, like if you're trying to remove an element from the container can't be empty, things like this. These are typically things that would be associated with an ADT. Also, ADTs typically, especially in the context of C++, typically make complexity guarantees. If you look at the C++ standard library, the vast majority of functions make complexity guarantees. Like this function is order n, or amortized constant time, or something like this. Because if you're writing code and you're trying to use some library, and if you're using C++, there's probably a reason you're using it. C++, I would argue, is the most difficult language out there to learn. It's a really complex language. Part of this is due to the baggage of trying to be backward compatible with C and still add lots of nice new features. But it's a hard language to learn. So if you're going to use it, you probably want to use it because there's a reason, not just, oh, for fun, let's make our life more complicated. And typically the reason people use C++ is efficiency. They need to squeeze the last bit of performance they can out of the hardware they're running on. So if you care about this, you probably compare a lot, if you are worried about this, you probably worry a lot about complexity. So for this reason, if you're using libraries, you want to call libraries in your code, you probably care about what complexity guarantees they make. So this is a really big part of abstract data type specifications. Like in the standard library, for example, often there'll be specifications of whether an algorithm is linear or logarithmic or constant time. A lot of things are constant time or amortized constant time guarantees. I have an example here, like an integer type. The values that can be represent are integer values. It provides basic arithmetic operations, relational operations. This is maybe not such a good example for complexity guarantees. Unless it's like an arbitrarily large integer type or something like that. In contrast to ADTs, we have an article called, oops, I guess this is on this slide here. We have what's called a concrete data type, which is just an actual essential implementation of the data type. So what I really want to focus a lot on are containers and iterators, because a lot of the algorithms and libraries are in C++ are based on the idea of containers, iterators, algorithms, this sort of structure. And so we need to understand a little bit more detail about containers and iterators and so on. Kind of covered some of the algorithm aspects of things already. So a container ADT, a container, or sometimes called a collection, it's just stores a bunch of objects, typically of the same type, like a homogeneous type of container. And typically they provide basic sort of operations, which don't have to, but typically would consist of, maybe as a minimum, things like what I've listed here. You have a way to clear the container, like empty out everything that's there, check to see if it's empty, like some kind of predicate for checking to see if it's empty, something for querying the number of elements in the container, something for inserting an element, something for removing an element, maybe something for finding an element in the container, depending on the container type. So these are typical sorts of things, and often you have like lots of other things as well, depending on the specific container that you're dealing with. In addition to this, often for containers, you want some way to traverse the elements in the container. And this is where iterator abstract data types come in. Iterators provide a mechanism for actually accessing the elements in the container. And I'll talk more about iterators momentarily. There's a few types of containers, like what's called an associative container, where it's essentially an associative container. You have a bunch of key value pairs in the container. You can look things up based on their key and you get back a value. It's sort of like an associative array, something like that, where the indexes are arbitrary types. They don't have to be integers. Containers can be ordered or unordered. Order just means that there's a well-defined order to the elements in them. It's not sort of very arbitrary. And I guess I mentioned at the beginning of the slide, containers can be homogeneous or heterogeneous. If they're homogeneous, it just means the elements in the container all have the same type. You can have like a more flexible kind of container that allows you to put elements of different types in it, which is what's referred to as heterogeneous or heterogeneous. And some examples of realizations of container ADTs, like in other words, containers in the standard library, there's quite a few of them, array, vector, and so on. The list goes on and on. What other things do I want to say? Oh yeah, containers can differ in quite a few different ways. And I've listed a few of the things here, the ways in which they might differ. They might differ in the number of elements they can store. There's some very simple types of containers that only can hold maybe one element, but they provide other additional functionality. Like it's not really so much that they're a container per se, because you're only ever putting one thing in it, but it maybe provides some other functionality in addition to being able to store that one thing. But more typically, most containers can store multiple things, because in most cases, you want to store more than one thing. Whether the values that are stored have to be unique or not. Some types of containers, you can't put repeated values into the container. Other ones you can. Whether they're associative or non-associative, which I talked about before, ordered or unordered, homogeneous or heterogeneous. Intrusive versus non-intrusive. The difference here, intrusive containers, like for example, if I'm a library writer and I'm providing access to some kind of container type and you're writing an application and you're using my container type, an intrusive container, if my container is intrusive, what that means is well, as the name sort of suggests, it's intruding into your life in the sense that there's some aspects of what you do in your code that's necessary in order to be able to use my container. There might be some special data members that you have to put in your classes that you're going to put into the container for things to work. So it's intrusive in the sense that some of the implementation is essentially exposed to you, and you may have to do some things in order to be able to use the container. Whereas non-intrusive containers don't do this. They don't really kind of expose any of their internals. Everything kind of hidden, and there's trade-offs between the two. Some are better for some things, some are more like critically used for other things. They may differ. Different containers may differ in their concurrency properties. Some may be thread safe. Some may not be thread safe. In other words, if you have multiple threads using the container, maybe for some containers you have a data race if you don't do anything special to make sure that you don't have multiple people trying to, for example, write to a particular element in the container at the same time, and so on. And there's lots of other ways as well, but this just gives you some sense of some of the ways in which they may differ. Then the other thing that are very much of interest again are iterators. Iterators are the way in which we give access to elements in a container typically. And the reason for using iterators in the first place, they're very useful for generic programming. Where, for example, you want to write a sort algorithm, but you don't want to write a sort algorithm for sorting integers and sorting doubles and sorting floats and sorting every other thing, so you write one. But that's not the end of the story, because when you're sorting things, you have a bunch of things. You have a collection. So it gets more complicated than just what type are you sorting. I have a bunch of ints that I want to sort that are in a C-style array. I have a bunch of ints that are in a doubly linked list. I have a bunch of ints that are in pick your favorite data structure. I want to write the sort function once. I don't care what kind of data structure those ints are stored in. I just want some uniform interface that interface I'm using, which is an iterator, it hides behind it what's actually going on to access the data. I don't have to worry about what data structure it's stored in. I just say, give me the next element, and it gives it to me. So this is very useful for generic programming. And because I would argue, I mean, some people like to go on and on about inheritance in C++, and I find that these people typically are Java programmers. The most important functionality in C++ is not inheritance, it's templates. It's all about templates, really. And I think that's somewhat, I mean, this is maybe a bit subjective, it's my opinion, but if you look at a standard library, there's probably a whole heck of a lot more templates going on than there is inheritance. There's some inheritance, but there's a lot of templates as well. Anyway, so, and again, because templates play such a pervasive role in the language and generic programming in general, iterators are very, very important, because you don't want to be writing, repeating code over and over again, so you can use it generically with a bunch of different types of containers. You just want to write it once. And iterators are the mechanism that allow you to do this. So what exactly do I mean by iterator? I mean, iterators are typically a type which is provided as part of the interface of a container class. Like the container ADT will provide some kind of iterator type. And typically it will provide operations which are kind of pointer-like. If you've used a language with pointers in it, which hopefully you have, you should know something about C++ if you're taking this course. You can like dereference an iterator, and that will give you an access to the element that it refers to. You can maybe go to the next element in the collection of elements that the iterator is associated with. Maybe go to the previous element, maybe skip ahead by n elements. Not all iterators provide all of these things, but it just gives you a sense of some of the operations you might use. So they're very basic. It's just allowing you to kind of navigate the collection of elements that the iterator is associated with. And there may be some limitations that are imposed, like maybe you can only go in the forward direction. So you can iterate over things in one direction. You can go through them in whatever the forward direction happens to be. You can't go back up and say what was come earlier. Maybe you can do random access, so you can kind of jump all over. So there's different types of iterators provide different functionality in that regard. Different types of iterators may impose constraints, like you can only maybe read the value once. Like you can access the thing the iterator refers to once, but then you can't look at it again or write to it again. Other ones, maybe you can do as many times as you like. And just some examples to finish off the lecture, just some examples of iterators. Most container classes, or actually probably all container classes in the standard library and a lot of other libraries as well, they have types that are members of containers types called iterator and const iterator, which are basically iterators that provide some iterator functionality for the container. For example, std vector and std set, which are indicated at the bottom of the slide here, they are examples of containers that have these types defined. And you just use them, and they know all the internal guts about how things are laid out in these data structures. And you just say, like, dereference this iterator, give me what's there. And you don't have to worry about how things are laid out. For a vector, obviously, it's pretty simple. But for a set, is probably something like a red-black tree or some other kind of relatively more complicated data structure, and you really don't want to have to worry about how things are laid out in memory. You just want to say, give me the element and let me do my thing. And I guess that's it for today. Any questions? Okay, don't forget the tutorial starts today, so there's actually a tutorial this afternoon.